So to start things out, I want to come to John Ruff's celebrated bus engine example as a way of, for some of you, probably refreshing your memories, and to others, you just introducing this stuff. Here we have a guy who's thinking about whether he should replace a bus, Mr. Zerker, or whether he should advance the bus mileage by 1 unit to keep this nice and simple. He's choosing one of these two actions, and before he sees today's epsilons, he's thinking about how do I maximize this expected thing, which I'm going to call the social surface function. Buses in this case are going to be differentiated by a fixed characteristic. And there are going to be some choice-specific disturbances over here, and here, that reflect the fact that econometricians obviously can't explain everything, and what gets left over is treated as an unobserved variable. So if we were talking about a simple logit model, we might imagine that there's no sums here, there's no expectation here. We just have a u plus the epsilon 2 and another u plus the epsilon 1. But you all know, I would think, that you can't measure a person's utility level. You can only measure the differences between utilities. Economists don't care about how well off people are. What they care about is what kind of choices they will make given the constraints that they face. And so that's why over here we haven't got anything related to the systematic part of the utility, just the epsilon, and these thetas and theta 1 and theta 2 represent kind of differences that you get from making the second choice rather than the first choice. Excuse me. So that is the problem that Mr. Zerker is facing. And a lot of dynamic discrete choice models have that kind of flavor about it. You've got an expectation out the front. You've got some discounting going on here. You're getting some utility that are going to depend on the state variables and systematic stuff. And there's some disturbances left over that we need to use to accommodate what we can't explain exactly. So we define the conditional value functions as for each choice. They're going to play a big role in a lot of this analysis, both for this, well, several of the lectures actually. The thing in which we look at the systematic part of the utility that you get today, plus the expected value of what the surplus function will be tomorrow when you take a given choice today. Okay, that's what this conditional value function is. You can see here's the systematic part of utility for the second choice. Here is the systematic part for the first choice. Notice that the first choice doesn't have anything here in current utility, so that's why it's just beta. And what you're going to do if you replace the engine is that you're going to start off again. So next period, you'll have just 1 mile on it because it will have done 1 mile. Whereas if on the other hand, you maintain the bus, you'll have another mile on it. So these are the miles that you've already got. This is the type of bus engine. You'll have another mile on it. And that's how it's going to progress next period. Okay? So that is our setup for Mr. Zerker's bus garage. Now, suppose we have a cross-section of a bunch of buses, and we know their fixed characteristics, and I'm just going to modify John's analysis just a little bit by pretending there are both Fords and GMs there, and although that's kind of dated these days, should have, well, anyway. There are American buses here, not Mans and stuff. So that'll determine their fixed characteristics, and so they'll have different kind of maintenance characteristics. They have engine miles on it, and a decision that's made each period. notice that you pick one of these decisions. Either there are spare seats, just rush in, grab, try not to run me over, and sit down and get here on time next time. Ooh. So you can only make one of these decisions. So the sum of the D's is equal to 1. See over there and down there? I've got a few seats there, guys. So we'll let the conditional choice probability be the probability that they actually make one decision versus the other, given the state variables or the observed variables that you see, but integrating over those epsilons that you don't see, okay? As a probability. Now, in this setup, what we have is that the probability of replacing an engine is just found by, well, what's the optimal decision going to depend on? It's going to depend on not only the things that we see, but also the things that the bus engine guy sees, as Mr. Zerker sees as well. So obviously his decision's based on the observable and the unobservable. So we're integrating out what we don't see. And here's a distribution for the unobservable. This is the vector here, actually, that consists of epsilon1 and epsilon2 from back here, okay? And so when is he going to do it? He's going to do it when, well, here's the systematic part of what you'll get if you take action 1, and then put that over here, and you've got the systematic part from taking action 1, current utility, that the observed stuff, plus the expected surplus function for next period, plus the epsilon associated with that choice. And then alternatively, if you've taken the maintenance decision, well, then put this over here. Here we have the unobservable for the maintenance decision, as well as what you get that depends on stuff that we see, namely we see, econometricians see X's and S's. And so you will take the first action, in other words, replace the engine if in fact the value from doing the first choice is bigger than the value from doing the second choice, in other words, the maintenance, okay? And so that's why this is an indicator function there. And then we're saying, well, let's integrate over these epsilons, which we don't see. That'll give us our conditional choice probability. Again, standard stuff that would, or a nice example that generalizes quite simply. Now, in the logic case, we have a nice way of getting at that. And that comes all the way from Dan McFadden in terms of the random utility models, static random utility models. Think of this as just the current utility for taking action 1, current utility for taking action 2, no more future. Think about that one, and then you would know from looking at your random utility stuff that in this case, we just have a logic type formulation, and so that probability then that translates to 1 plus this differences in these exponential terms, right? So nothing new here except the fact that we've kind of got most of the dynamic stuff inside these B's as opposed to having a static model. Well, John showed, and you can generalize this formula, that if we look at the difference between what's called the social surplus function, remember that the value of the lifetime utility, but before you see today's epsilons, is equal to the conditional value function, which is kind of like making a choice, or it is making a choice. What you get from making this choice minus the log of the probability plus this Euler's constant left over. And think about it really closely and think, well, what happens if log of P, what if P was equal to 1? Okay, if P was equal to 1 or really close to it, this would almost be 0. And the social surplus function would almost be equal to the conditional value function, right? On the other hand, if this was 0, whoa, the difference between this and this would be huge, okay? And so you would see how this probability is kind of adjusting the conditional value function to get that difference, to get that loss that you incur by making a choice without thinking about it. So the conditional value function of not replacing, let's just go to the algebra for a minute, is going to be equal to, here's your current utility, the systematic utility, plus the social surplus. And then what is this social surplus thing? Well, we just plug it in here for next period. See how we've got that in there? Okay, just plugging it in. And that's what happens if you maintain it. If you replace, you've got, well, nothing systematic here because this is, remember, a net of maintaining and up versus replacing. So you've just got this guy in here. And notice that now you're going to have, it should have been an X, see this, S plus 1, X plus 1, S, all right? I make the mistakes. Your graduate students, you fix them. So here's a conditional value function for the replacing, and now we do the same thing here. Next period, we're going to have this one coming in like that, same thing, but now it's just 1 instead of X plus 1. But now, think about what happens when you replace a bus engine, okay? In Mr. Zerka's world, the seats look the same. They never degrade. They're great. The only thing that goes wrong with a bus is that the engine dies, okay, eventually. So if you replace the engine, you are starting out with effectively a new bus. And not only that, it doesn't matter how many miles was on the old bus. That's irrelevant. The paint is still beautiful. And so are the seats. It's only the engine. And so that's why this is called a renewal problem, because it is if you are starting your life again. I wish. Okay? So in this case, it doesn't matter whether you've got X plus 1 miles on it or 1 mile. If you're replacing, the conditional valuation function is the same. And that is nice because that means you can kind of look at this guy and subtract this guy and really simplify what's going on, because this one is going to cancel with this. See that? And this guy is also going to go, okay? And so when you're looking at it, you're going to have V2 minus V1. Well, you've got this stuff out here. And then you've got this log probability that you've got to worry about, and another log probability that you've got to worry about. But that's it, okay? So let's do the subtraction. And after all the hand waving, this is what you get, okay? For the reasons that I just said. And so now we can then ask, well, how do these probabilities work out? Well, then you can get this probability working out this way, because V1 minus V2 is that, and I said something about what those conditional probabilities were. Here it is, today. We already talked about that a couple of slides ago. So now we have this guy, that guy, plug it in, this stuff which is on top, all right, because they're logs. And so let's see what we've got here. Probability of replacing the engine. Well, this is just a logic. Here is our current utility stuff. Okay. And all we have is some stuff that depends on the future. Okay. Because it depends on the future, it's going to be discounted by the beta thing. And so really, we're thinking about the conditional choice probability in this dynamic setting as being what you would get in a static model, but with this offset term to reflect the fact that, no, wait a minute, maybe we should think about the future. Okay? And that's an argument that economists use all the time when they say people are rational when it comes to making the most important choices of their lives in an experimental classroom setting, makes no sense to think too hard, because what happens after class is over is way more important. Okay. So that's the sense in which we've got these conditional value function being able to being similar to the utility for a current utility, but taking into account the future. They're taking into account the future through these conditional choice probabilities. It turns out to be a general result we'll talk about in a minute. So what you could do is just go ahead and do maximum likelihood estimator, because here's a probability. Here's other probabilities you can solve for the discrete dynamic choice problem for each of the parameters, and just go ahead and estimate it that way. And Bert's going to be talking about much more complicated models in which you can do the same kind of thing this afternoon. We consider the following CCPS. Those we just take some relative frequencies. What's the chance, the probability, the relative frequency that they'll replace the bus when they've got this many miles and it's this type of bus? Well, that's just this frequency estimate. Okay? Plug it in here. Okay? Put that frequency in here. Okay? Do that. Correct the standard errors because you're doing a two-stage model. I'm assuming that you guys have Econometrics 1 here, done some nonlinear estimation. And so if you've done some nonlinear estimation, you've probably done an estimator in which you estimate something in the first stage, you get that first stage estimate in, you plug it into the second stage, do a second stage estimator. The reason why you do that is because it's computationally fast. Okay, so now you've got just adding in this. These are numbers, of course, because you've estimated these as probabilities. You put these numbers in here. That's your offset term, a numbers, put them in. Then just go ahead, do your logic, and be done. So here's a Monte Carlo study. And my colleagues tell me it's a little bit out of date, which it is. But I still want to make the point, because when I get my graduate students to do this, everything's speeded up, but the differences are still there. Let's suppose that there are actually half of them are Fords and half of them are GMs. Right? And for now, I'm going to assume that that's observed. Tomorrow, no. Okay, but for now, total accumulated mileage, it's just going to proceed according to a random variable. Okay. That random amount is going to depend on how much, obviously, what the routes are being taken for the next period. And it's sort of like a discretized version of an exponential distribution, in which instead of doing like this, you go clunk, 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 put that in, all right? And then how far the nature of that exponential distribution is also going to depend on whether it's like this or whether it's like that. Okay, it's the advantage of real-time stuff in hand wave. So that is the distribution from which these deltas are drawn. Okay, in other words, it's just adding a little bit of complication to it to show how the state variables change. And the other thing we might do, and we've done, is to just allow for the fact that the maintenance costs might be tied to vintage. In other words, we've got some non-stationarity in there to reflect the fact that the cost of replacing the engine are actually going down. But in this world, in a thoroughly anticipated way, and I'm going to come back to that assumption later on, it's going to make things much easier, of course, but it also makes the optimization non-stationary. Think about solving this backwards induction problem if this thing is non-stationary. Okay. And so the payoff difference is just going to be this difference. Here we've got, after you get to 25,000 miles or 250 or whatever it is, in terms of scaling it, the maintenance cost is the same. That's what we're saying. And otherwise it's increasing by this much. And that will mean in this world that if you difference these conditional value functions, take my word for it now, check it out later, you get this thing later on. That's what I've done here. Okay. So how does this work? Notice that we're estimating the discount factor in here, but that makes the optimization problem non-trivial because it's sort of pretty non-linear because of that. Here's our data generating process. We're always thinking about in econometrics a data generating process. I don't care whether you're doing some kind of dip in dip regression or whatever. As soon as you start putting probabilities in there and do some statistics, you are talking about where did that data come from? Now, we happen to be economists. And so my argument is that we should be using all of our arguments here, and that's why we're here taught to teach, is that the statistics that you get should reflect the economic model that you start with. That's what we mean by structural, okay? That we're taking seriously the notion that a model is just a bunch of assumptions put together that make economic sense or not, okay? And so that's in some sense how we describe what's going on. So here's our data generating process, and you already know what the model is in this case. It's Mr. Zerker's model, okay? And you can see that the data, the estimates are roughly the same, and the standard errors are roughly the same. The main difference is this: it's huge, and it still is, although it's way down from 130, but still plenty when you've got beta in there estimating. And whereas this is a few seconds, okay? And it's easy to see why. In one case, you're solving the dynamic value function, and in the other case, you're not. You're just putting in some potentially poorly estimated relative frequencies here, which you're not really interested except to the extent that they do a decent job of correcting how the future affects the agent. Okay. That's it by way of introduction. Now I want to sort of give you a more canonical approach to where we're going. So here's the standard setup that you're going to see in one form or another throughout the next few days. Got time discrete, but it's more to the point. It is a point process, so it could be a Poisson arrival event that's either neither here nor there. For the moment, these are the states, look, revealed to the individual, okay? Not me or you, the econometrician, to the individual, all right? And there are individual choices being made. A transition function that takes you from today's state variables to tomorrow's state variables when you take an action, J, one of those. No loss of generality by assuming they're mutually exclusive. And for each of these choices, dt is this whole vector. Only one of these is 1, the other is 0. So that means that only one of these u's counts, namely the u for the choice that you pick. You get some current utility that depends on the state variables, and everything else is relevant again to the individual, okay? This discount factor is kind of not important here. It's really a way of thinking about bounding the stuff. We've already subscripted things like tau, so we don't really need it, but it's one of the reasons why it's there, the beta is there, is because we're going to parameterize things like crazy down the line anyway. And so in that case, we'll typically take some kind of discounting here. And the expectation is chosen over, well, what can happen over the next few periods, right through to the end, given the information that I have at T. That is the way of thinking about this stuff. You have some information at T. You're thinking about the future, conditional on a bunch of choices that will produce an expected utility. You can integrate over the choices that you're likely to make, and that then gives you back what your expected value is going to be for the life. So here is an assumption that I'm going to go with, and a lot of stuff widely used in estimating dynamic discrete choice models, both at the individual level and also at the multi-player level. Often used. Often. Very often. Here's the idea. We're going to decompose what the individual sees into two things. And this is why I had the U star back here. You notice I snuck in a U star on this stuff. That was because it was the individual's problem. Now I want to divide it up a little bit into kind of the systematic part plus the non-systematic part, and using the language or the notation that you will see in most of the papers that get written here. When I say written here, I mean published, and by anybody. Here you've got an observed variable. I'm keeping this finite, not necessary to do that, but it does change the asymptotics a little bit, because now when you're thinking about conditional choice probabilities, you can have to smooth rather than just take relative frequencies. In fact, even when people are doing when they're only state variables, there's also smoothing going on. And there's a question when you're using categorical variables, are they close to each other or not? And so does smoothing make sense? There's an epsilon here for the unobserved variable and a density for the epsilon. We're going to call this the probability density for what's going to be an unobservable conditional on the xt. You can just define it that way. And likewise, I'm going to define a transition density for xt plus one conditional on xt. So we could imagine this stuff as margining things out, all right? But this is how I am defining the probability density, epsilon conditional on xt, and xt plus one conditional on xt. Of course, if we were to take the most general setting, we're kind of going with the z's. Next period z is going to depend on this period z's. That's everything that's relevant for the individual. And so that is why we would be thinking about the x's and the epsilons for this period as well. How is that going to transition to the x's and the epsilons for next period? All right. And so the conditional independence assumption says we're going to make this one. We're going to make this assumption, okay, that the f's only going to depend on the xt plus one's only going to depend on the xt. That's the first thing. Doesn't depend on the epsilons. And the second thing is that the epsilons don't depend on last period's epsilons either. That is the second thing, basically. I mean, the formula says it precisely. I'm giving you the intuition of what really counts out. So that conditional independence assumption enormously simplifies the kind of problem that we deal with, and it's used all the time. Now, you might say, gee, is that realistic? Well, remember, models are a bunch of assumptions put together. We are not looking for truth here, guys. We want to get paid. Okay? So we have to produce something that people find valuable. That does not mean truth for those of you who believe in such a thing. Okay? Because that is faith. So the idea is that we're actually coming up with something that'll assist people, that there's actually demand for our services. Remember, we're economists, we believe in that kind of stuff. And so that's the sense in which we put together assumptions that help us to get somewhere. There's a good reason for looking under that lamppost for lost keys, because everywhere else it's dark and you can't find anything, okay? Very limited, but that's the only choice we have. So that's how I would be justifying any kind of assumption in dynamic discrete choice analysis. And when people say, well, your model is not realistic, the first response is, well, what kind of realism is in your head? Person who asked the question. Second assumption, second point is, what's so realistic about anything that you assume? Okay. So there's no reason why people who do structural econometrics have to be held to a different, I won't say higher, different standard than everybody else. We're all making assumptions about what are we assuming about that data generating process. Do we want to have something that is, I'm going to say, internally consistent, makes mathematical sense as you follow the steps through. All right. So here's the social surplus function. I already talked about it before. You've got the x's in here. You're integrating over those epsilons. And then you've got a conditional value function being systematic part of utility plus what happens to the next period social surplus function. Yeah, we actually, well, integrating over the choices that people make. We define the conditional choice probabilities in the way that I described in the Harold Zerper problem. Just integrate, in other words, just integrating over the unobserved stuff. We can push further, and Victor's going to be talking about more about this later this week too. Suppose we've got a dynamic game. Got a bunch of players in here, and each of these players is making a decision. So we could think about the decisions, the choices of all the players in period T, and in the end, we're thinking about, well, it's a non-cooperative game, so each person is maximizing their own problem in equilibrium, which means that everybody else is playing their equilibrium. And the definition of Nash equilibrium, or some of the refinements, is what's my best reply to what everybody else is doing. So for that reason, let's look at the decisions of everybody else, choices of all the other guys. And the value of the state variables in this case, of course, are not just the things that affect me, but the things that affect everybody else as well. So my capital, my rival's capital, environmental agencies' rules, whatever, okay? They're all in there. That's what the X is, okay? And we've got a transition here that I want to kind of highlight, because we're going to be using it in this kind of setting. When we're estimating these kind of models, we're again focusing on what does the individual do to maximize what's good for them, given what everybody else is doing. And so we'll talk about the transition of what's going to happen to the whole industry, given that the whole industry is like this now, and everybody else does whatever they're going to do this period, along with what I do. Okay? So we'll talk about that transition. And the reason we're talking about that transition is, well, I'll get to it in a minute. So that's the transition. Yeah, let's move on. So when we think about player I playing this game, he gets a big utility. We notice a capital U here because I'm going to have to simplify things in a minute, pull it down. Depends on the choices of everybody else. Okay, depends on what you do as well, what the state variables in the industry are as well. Okay, and my little epsilon JT. Okay, because that thing is going to affect me, not going to affect anybody else. So let's now think about the choice for the single person, for a single, similar to the single agent setup. We just define, well, what's the probability Mr. I will take the J choice, given all the industry variables, as here he is. Here's the choice that he'll take when he's integrating over the epsilons. Okay, so I'm going to define the CCP almost the same way. And then there's this transition, which it's not going to depend on just the environment, on how buses wear out, but also how everybody else will react. In some sense, everybody else is part of the environment that an agent faces when he makes his choices. He's making an individual decision, taking into account the effect of people's actions on him. He understands that he's going to affect other people's actions as well, and as a result of that, down the line, this might come back to haunt him. But and he takes that into account when he's thinking about his value function. So here he is. Here's the probability of everybody else making a given set of choices, given that the industry walks into this capital, walks in with this amount of capital. This kind of thing is, I'm going to say, fundamental to the way I try and teach my MBA students strategy. I am really asking them, you can't just look at what's going on to yourself. You've got to take into account the effect of everybody else on you, okay? And so when we're talking about big decisions, if my MBAs are successful entrepreneurs or businessmen, I bet they will be doing that. The failures won't listen to me, but they won't be important anyway, because they won't really be affecting very much, okay? There's a sense of a little bit of evolution in this as well. So, in a sense, we could think about the equilibrium. We could just talk about, and Victor will go into this in more detail later on. This is going to be an equilibrium if, in fact, we take the actions of each of these individuals and they are solving the optimization problem that I just talked about on the previous page somewhere. I thought I did. It was supposed to be there. In any event, we're solving this optimization problem that they solve. They're maximizing their surplus function. When we define the little utility now as being equal to the expected utility that I get from taking action J, I'm Mr. I, when the industry variables are XT and other people make these choices. I don't see their epsilons, okay? I only see my epsilon. We simultaneously make a decision together. Simultaneously just means that I have to move before I can see his epsilon, not that we have to move like that, okay? It's a statement about the information set, not a statement about the calendar timing, okay? That's important here. So we're simultaneously making these decisions, okay? And and this is the utility that I get when I'm looking at the probabilities that they will make whatever decisions they make, okay, in equilibrium. And of course, transitions will move forward according to, again, I don't know exactly what they're going to do, so I've got to integrate over what they're going to do when they're making their choices. So we've now got little u and little f, very similar to the situation that we had in the individual optimization problem. So, in fact, they have this analogous interpretation. Best applies to a dynamic discrete choice problem when the equilibrium, and I'm thinking of Markov equilibrium in this case, is played out by the data generating process. So now I want to start talking about some of the properties of these kinds of models under the conditional independence assumption. In other words, when can you plug in P's all over the place and expect to get something that makes sense economically when you're thinking about the econometrics of the problem? So the starting point is to note something that we already saw in the Rust example, that we could look at those differences in value functions, and they were really closely related to the choice probabilities themselves. There's a logic transformation, and that's how you got it. It turns out to be a pretty general property. So to find the differences in the value function, the conditional value functions, and notice again, the reason why we're looking at differences in conditional value functions, because we don't care about levels, we care about differences, because it's differences that determine choices, okay? Do you get more utility this way than that way? So there are a bunch of different, they're all linear combinations of each other. And so why don't we just set a basis functions? In other words, let's just define the differences relative to the cap J's choice, okay? Could be the cap J choice. And we're going to define each choice relative to that one. No, he's not going there. Yes, he is. And so that would mean that any difference between the little j's and the little k choice is just the difference between those two. Okay, that's just linear algebra. So looking at the conditional choice probabilities here, we know that this is just taking a value of 1 or 0 when it's optimal for the person to take the jth choice versus not. We're integrating over the stuff that we don't see. We've already managed to kind of knock out all the other variables that might influence epsilon. It only depends on x. And so we're putting in here these indicator functions that I did for the Mr. Zerker problem. Notice now that all I've done is subtract. You see, what I did before, let's look at this just a little bit more closely, was I didn't have the triangle in there. I didn't have those triangles there. And I was just looking at V little j plus epsilon j, and there should be a t, well, we're going to integrate over these anyway, is bigger than V little k plus epsilon little k. Okay, that's what we did before. And now I've got deltas in front, okay? But all I'm doing is putting this guy negative and positive, all right? Subtracting it off here and then adding it back here. So it's the same. And so now we've put everything in terms of the deltas and that's reflected in the fact that the probabilities must sum to 1. So once you know cap J minus 1 of the probabilities, well, obviously the last one is the one that's left over, and that's why we're only looking at the differences in the value functions as well. Okay. Conditional value functions. So by definition, what this means is we've got to integrate over this region, okay, to get the probability that it takes the J. And so all we've done here is just integrating over the epsilon so that this inequality is satisfied everywhere. Okay. So that we get this indicator function being satisfied, and that's why this is written that way. We notice the multivariate density of this thing is just the cumulative distribution function differentiated by each of the epsilon. And then we could define just the derivative of the cumulative distribution, whether it's taking that derivative with respect to the epsilon j. And so now we'd be integrating everything through apart from the epsilon j up to here, here, and here. Okay. So we're integrating up over this region, you know, for all the other epsilons. And then that is for a given epsilon j. And then we're just integrating epsilon j over the whole thing. All right? And so that's how we get this formula here. This is just another way of expressing this. Okay? This is just another way of expressing this guy. So now we'll think about the following thing. Why don't we interpret this Q as just integrating over the epsilon as before, these GJTs, see, from the previous page. Okay. And now instead of putting delta V's in here, I'm just going to put in, what's that? Delta, right? What is it? Delta? Yeah, delta. We can interpret this as the probability of taking action J in a static random utility model where the payoffs are delta J plus epsilon J. Okay. Because really what you're doing is instead of putting delta V's and things, you're just putting in deltas. Okay? Do it another way. Instead of putting triangle V's in here, you put in deltas. Okay? That's all I've done. And we already know this is the conditional choice probability for a static model as well. Okay? So why don't we just put in these deltas? Mm-hmm. So that's the sense in which we can interpret this as this. When I say can interpret, what I really mean is this is what we would get if we had people facing a static model, delta J plus epsilon J, and they chose the optimal thing, and we were integrating over the epsilons that we don't see. Mm-hmm. So in that case, we can see that this is going to be between 0 and 1. They're going to sum to something that is less than 1. And obviously the difference is going to be the probability that you take the cap J term. And so what you've got is that this Q, if we replace the deltas with the triangle V's again, we would just get back what we talked about before. Mm-hmm. It's almost language. Basic point is there are as many P's as there are deltas. See, the J-1 vector of these deltas, we're thinking about all the P's that would be different. The last one is a linear combination of all the others. So there are cap J-1 deltas, cap J-1 P's, and this turns out to be an invertible in delta for each. In other words, you tell me what T and X is, then we get this invertible. So this implies that the delta V's here can be written in terms of this inverse function. Okay? That's what that's saying. In other words, rather than solve for what these are, let's take it as a given that the agents have already solved the problem for us. That's an assumption that we made going into this. They were acting rationally. Why do we think they were acting rationally? When, speaking for myself, I made lots of stupid mistakes. Because I don't have a nice axiomatic theory of how mistakes get made. It can explain too much. You can say to your the firm who's employing you, anything can happen. And do you know what he would pay me if I said that? 0. He already knows that. You've got to say something that has what we call empirical content. The model must be rejectable in some way. And so that's where the rationality comes from. In fact, when we're economists, the argument would be, yes, we are definitely making a mistake when we are assuming that these people behave rationally with the data that we've got to look at. They actually have way better data than us. They're making much better decisions that we would probably make on their behalf if we were just using our models to predict what they would do. That's the sense in which rational expectations is a little bit off. It has nothing to do with people being stupid. It has to do with us not being able to really get to everything that we would like to know about these people and spend as much time as they spend on making their important decisions known, and hence being able to predict as well what's going to happen to them, okay? And that's the sense in which, again, I talk to my MBA students, I'm not smart, I'm just specialized, okay? And it's going to happen to you too. It is already happening right now, okay? Because you are getting training in a particular type of way of thinking that hopefully has value to the rest of the world. Okay, so far, yes, it does, I can tell you. So, okay, this is what the inversion theorem implies. Okay, this inverse has an intuitive interpretation. Given X and conditional choice probabilities, agent is different between these two choices of for values of epsilon jt prime and epsilon jt cap jt prime, satisfying this. Okay, you're indifferent if this is equal to that, right? That's it. Do either thing. So that would mean the difference between this triangle V is just equal to those set of epsilons for which you are indifferent. Okay? And so that's the way to interpret the jth component of this inverse. It is giving you the set of differences for which you are, or the agent is different between these various options. So here it is. More generally, okay? Value of the spectrum mapping corresponds to those set of epsilons that renders the agent indifferent to all those choices. That's a way of thinking about what this inverse thing is. Why is it useful? Okay, first of all, we can get tractable representations of conditional value functions. In other words, we're going to see in a minute that we can get representations of the conditional value functions that exploit the fact that the people have already solved their optimization problems. We can get, so we've got conditional choice probability that will allow us to get around that backwards induction question. You can analyze the identification in dynamic discrete choice models within this setup, because after all, given the conditional independence assumption, the conditional choice probabilities themselves are giving you almost everything that the data has to offer. Everything else is independent and idiosyncratic. Provides the convenient parametric forms for generalizing, going beyond type 1 extreme value, and there's been a little bit of extension that way now in terms of the empirical work. I talked about a renewal problem a minute ago. I'm going to talk about finite dependence tomorrow, and then Victor's going to follow through with more stuff about finite dependence as well, so that we don't have to think about conditional choice probabilities from the beginning of a person's life right to the end of a person's life, but only maybe a few periods ahead. And to some extent, we can also deal with state variables by using this method. And there is, even today, there's just a job market paper. Well, Let's move to the first set. Let's see. I want to define the conditional value function correction as the speed of the social surplus function minus the conditional value function. This turns out to be kind of important in coming up with both the representation and also the identification arguments. So it's an object that just turns out to be useful, okay? Here's our social surplus function. Here's our conditional value function. And of course, in stationary settings, we could do that. And why do I call it a value function correction? We've already seen that taking the jth choice, regardless of what your epsilon is, could work quite well for you if it's optimal to almost take it anyway, or could work out very poorly for you if it's a choice that you wouldn't make ordinarily. So it's like, suppose you just took action J at the beginning of the period without looking at your epsilons, okay? It's an artificial device. I don't really model people that way. We don't. Then the expected lifetime utility would just be, here's your conditional value function and the expected value of the epsilon, given the state variables that you walk in. So if you committed to J before seeing your epsilons, in other words, if you didn't do the optimal thing by looking at your epsilons first and then deciding, but did it straight away, well, the loss that you would get is the difference between these two things. And here is what you would get if you look at the social surplus function, because you're going to do the optimal thing once you see your epsilons. Here's what you get when you take the jth choice right now instead of looking at your epsilons. So this is going to be equal to, by the definition, it's just going to be equal to your P of X. And then you just subtract off this expected value of epsilon. It's kind of like an unconditional expected value because it's not conditional on choice behavior. And so in fact, if this thing, which is not true for type 1 extreme value because it's the 0.577 thing, but if it was normal, you would have the expected value of this thing would be 0 and the loss would simplify to be equal to just that, okay? So that's why it's called a conditional value function correction. It doesn't quite correct because at least in some cases and in many cases that we look at in dynamic discrete choice, one there, no? Okay. There's a couple too. That's why we call it that, okay? So notice that I'm going to argue that this thing is actually identified. In other words, this object that we've defined here is identified from the data under some circumstances. These guys, each of these guys, no, because they involve levels. But difference, yes. Okay. So just expanding this out, here's V. What is that equal to? Well, you sum your conditional value functions weighted by the probabilities along with the epsilon that you're going to get if you take the optimal action. Okay. Over here, look, guys. Which epsilon do you get? Well, it's the epsilon that occurs only when you take the jth action. Otherwise, it's 0. So then, we're summing over the j's, but this one's going to knock out most of them. So you get this value when that jth action is optimal, and you're sort of slicing up. Here's our vector of epsilons. Well, over here, we take this action. Over there, we take that action, etc. So we get those the epsilons that are irrelevant for that one. Okay. And we're integrating over the density of epsilon at the same time. And then over here, we're just subtracting off VIT. Okay. Probability sub to 1, so we get VIT back. All right. But the difference between Vj and Vi is just equal to these two things. Okay, that's our inversion theorem. And also, if we're looking at this term, this set of terms, looking at the expected value of the unobservable that occurs when we take our optimal action. Let's go on. Well, what is that? Well, look at these optimal actions in here. Why are they optimal? Well, these are just the differences in the V's, okay? And now I've put them in terms of Q's because I've used the inversion theorem again. And so let's have a look at these. Let's have a look at these guys. If we know this distribution, notice big if. If we know, or in other words, put a parametric form that we model in there as an assumption, okay, like type 1 extreme value, then the P's are observed, and then we can do this integration, and so we know what the value of this thing is. And so if G is known, then then this thing is known too, because this is in terms of the conditional choice probabilities for which we've got consistent estimates. This is in terms of conditional choice probability estimates. So we have that being identified as well. All right. I'll get there eventually. Maybe I will get there eventually. I think I've run out of battery. All right, thanks. All right. Anyway, I'm doing all right. I think I'm okay. No. All right. I need to go back here. Here we go. Sorry. I want to make sure I've got this right. Yeah. All right, for the nested logit, we can see that it's a slightly more general function than the case where we've got just the logit set up. This correlation here, think it'll work then? Right? Oh no, you're not in yet. No, it's no, well, I'll keep going. For the nested logit, you've got some correlation, okay, between things that are inside the nest and stuff that is outside the nest, right? So when sigma's equal to 1, all right? When sigma's equal to 1, this thing goes all together, all right? And in that case, this correction only depends on the choice itself. But when sigma is not equal to 1, and there's correlation within the nest, you know, different types of, oh, I don't know, roots given that you're riding a bicycle or something, you know, going back to McFadden, then the correction factor is not just going to depend on what happens for the individual choice, but also what happens in the whole of the nest itself. So that's something that people are using to some extent these days. Still not a whole lot of action there, but there is some question. Now I want to show how we can use the conditional value function correction as a way of representing the value function itself. Okay? There we go. Thanks. Yep. All right. Here's our conditional value function. Okay? U that you get from this choice plus the expected surplus or the social surplus that you'll get from next period X, you don't know what it's going to be, so you've got to integrate over what xt plus 1 is going to be, given that you've taken choice J. Fair enough? Back on track? A little bit of detour there. So let's substitute out. All right. Let's substitute out for the VT plus 1 using the conditional value function that we got before. All right. Remember I said back here that the difference between the social surplus function, the social surplus function was equal to the conditional value function plus the correction. All right, said that. We defined it, we worked through it, why it was called that way. And then I said, this thing is identified. That B, that correction is identified. And then I said, in fact, this has a simple form in a bunch of cases. Nested logit, there are actually some others that it also can be worked out fairly straightforwardly, sometimes numerically, but it's straightforward. So now I want to substitute out the social surplus function with a conditional value function plus the correction. Okay. Now, what I could do is pick any old K, any action. It's still going to be true because this thing being equal to this thing is true for all of the actions. Okay? So we could repeat this procedure if we wanted to by saying, well, okay, what about VKT plus 1? Why don't we put that in here and put a UKT here and plus a beta V here with a K for the next period? Go through the same substitution for a same K or a different K, whatever K. Keep going. You could just keep on expanding this thing. And in fact, you wouldn't even have to think about taking one action or another action. If you think about it just a little bit more, suppose we took K with probability a half and K prime with probability a half, still true. Because V is equal to this for each of them. So obviously, provided they sum to 1, the weights that we put on each of those actions sum to 1, we're in good shape. They don't even have to be positive. And it turns out, and this is going to the finite dependence stuff that we'll talk about later, that putting on negative weights is actually quite important in some cases. I'm sorry. We will get control eventually. So let's have some weights here. These weights all sum to 1, but they could be negative. And those weights are going to induce different paths. I am not suggesting that putting these weights on are in any sense related to the optimization problem that the person solves in the first place. The purpose of the weights is to make the estimation easier in some sense that I'll talk about down the line. It is not, the person's already solved their optimization problem. We are putting on weights to make things simple for us, okay? And at the moment, I'm just playing with algebraic formulas. That's all I'm doing, okay? So we put some weights on, and when we put those weights on, that is going to push people down different paths. And so if they start out at XT, and then they take action J, and then they follow through with a bunch of weights, then this is the weight or the probability that they will get to X tau plus the X tau, so given X's at tau plus 1 periods later, okay? You could write this down in matrix form. All we're doing is taking set of weights and then moving that matrix XT from here to here to here, following through with it on this weight. Okay, I've written it up here as just coordinate by coordinate. So here's the thing. That the conditional value function is just equal to the utility plus you pick any old weights out there to the end of the person's life. Later, we're going to talk a bit about what weights is useful to pick. You pick any old set of weights out there, run them out, and this is what you will get. Okay? So, basic point here is that you've got the conditional value function being equal to the utility, current utility, plus weighted future utilities, along with value function corrections. Remember, the reason we have to have value function corrections is because we're picking weights that have nothing to do with the optimal behavior. And so we have to have those T's in there. But we already know those T's are identified. It's like walked through an identification for a couple of slides ago. And so now we have a setup that if individuals have already solved their optimization problem, then their decisions are going to be, as reflected in the CCPs, are going to be informative about their value functions. So much so that you can write down the conditional value function in terms of current utility, future utility, value function corrections, weights, without doing any recursive maximization. See that? No optimization involved. The agents have already done it, okay? The agents have already picked what's optimal for them, and we are just leveraging off their optimizing behavior when we write down this representation. So let's go to identification. I want to identify the, write down some identifying assumptions for the data generating process, fully characterized by what are we assuming about the current utilities? What are we assuming about the disturbances, how they move? You know, this is the type 1 extreme value. This is often linear. What are we assuming about the F's? Sometimes we're thinking about a deterministic world where you go with next period state depends entirely on this period state and the action. And then the discount factor, we often actually assume that. We often assume that's a number. And then there's the finite horizon. That fully summarizes the model. Once we say, well, here are the things that we're assuming about the model. It's one of these objects. Once we've said enough about that, we've got a model on our hands. And so we've got observations, either a panel or a synthetic panel. In other words, people that look like each other, but just in different age. Let's not worry about what I mean by this for now. And the decision outcomes, okay? And we're going to assume that we already know most of this stuff. So we know whether it's an infinite horizon, time horizon, or how long they're going to be, what T is. Could be stochastic, could be driven by a stochastic process. Maybe we'll assume for now that we know what the discount factor is. And this F is coming straight off, well, that's how the X's move. So XT, you take an action J, that gives you X, the XT plus 1 with different probabilities. So we can estimate this thing outside of the model, okay? In other words, we can just look at the actions and the choice. We look at the choices that are made and whether they're optimal or not. And we look at the X variables, and then we can just get the relative frequencies of how things evolve so far as the X's are concerned. And the G's, we typically assume we know, almost always assume that we know, and almost always we assume that they're type 1 extreme. If they're not, if they're nested logic, then there's a parameter in there, the sigma parameter, and then we would actually want to estimate that sigma parameter, of course. And that's going to raise issues about what else we have to assume in order to estimate the sigma parameter. Get to that later. So goal is to estimate U, and this is typically how most of these 95% of these models go. We're trying to get out the preferences, the U preferences from decisions that people make, state variables they have, when this is known, or in this case, when this stuff has been already estimated from outside the model. This is clearly identified under the conditional independence assumption, and that's why I'm not talking about it right now. First point I want to make, widely believe that U is only identified relative to one choice per period for each state. I'm going to say this is true because I can see I'm a little bit running out of time here. So I want to economize on some stuff, spend more time on other stuff. Okay. In other words, we can normalize one of the utilities, give it an arbitrary value for one of the choices in each state. Okay? So we've got X states here, cap X states for each period. Okay? If it's non-stationary. We're going to say, well, let's normalize one of the choices to be, say, 0. And that's what people often do, actually. They'll often say, let's imagine that one of the utilities will just set to 0, and they actually say, then we'll consider everything relative to that, which is not quite true, because in a static model it is, but in a dynamic model, it's a little, that interpretation doesn't quite hold. But in any event, let's do that. And then consider the probability, the conditional distribution, we'll call the probability distribution from xt plus 1, Cal plus 1 onwards. For example, taking action J in period T, and then the normalized action from then on out. Okay? So we're going to take a normalized action once we get started, but action J to begin with. And that's why I've got a K star there. Well, in that case, what we can say is the following. And I'll just intuitively talk about it rather than go through the algebra. First point is, suppose all the utilities are defined in terms of, well, here's our normalized action, and this is the star utility that we get. So we're taking a normalized utility, putting 0 on this, and then defining the utilities in this way. Okay. If we do that, it's observationally equivalent. And the other side is that if you've got two things that are observationally equivalent, you can always use this representation to talk about those two sets of utilities. In other words, intuitively, when we can only identify up to one of the utilities for each of the states and each of the time periods when we're talking about a non-stationary model. And that is for a given set, for a given assumption about the disturbance terms. It's important to recognize, I think, what the assumptions are behind the models that we build, because that helps us to determine whether we should come on strong or not so strong, depending on how confident we are in the assumptions that we make at the front end. So this basically produces the identification result that if you know the payoff of, say, the first utility, first choice, or more generally, you're willing to assume it, then the utility of all the other the utility of all the other choices at all the other states are identified because they only depend on the conditional choice probabilities. These correction terms are identified, okay? So that's where they're appearing here and here, okay? And we can then get this in a finite horizon case by thinking about, well, what's the what utility will you get in the last period? And then plug that in. What's the period? What utility would you get in the previous period? This is an identification result, not something that you'll do in estimation. So suppose you didn't put any restrictions on the utilities, apart from the fact that you'd assumed your G, that's your disturbance terms, your T, the amount of time it would take, and you already knew your Fs. Or let's suppose you didn't use your Fs and you just used cell estimators on your Fs, got your conditional choice probabilities there. Okay. Central limit theorem, both of these have asymptotically normal distributions. These are both maximum likelihood estimators. Okay, unrestricted. They obtain premier bounds, lower bound. U is exactly identified now. That's what the previous theorem shows. So it must mean that the U hats that you get out of this representation are consistent and asymptotically efficient. Okay. So it contains the premier lower bound. What that really means is the following. That the only way you get more efficiency is by making functional form assumptions on the U and the F. Okay? Nothing wrong with that. We all do it. I'm not saying you shouldn't do it. What I am saying is that's where the extra efficiency is coming from. And why do you do it? You put more assumptions on so you can get more precise estimates. That sounds like a very reasonable thing for me to do. But that's what's going on. So in practice, yes, we put on parametric assumptions on the U's and the F's. Okay. And then we go ahead and now we're defining the model in terms of time of the horizon, the discount factor, the thetas, and the disturbances. And then we say, okay, this is where our model comes from the interior of this set. Often we assume that U is just linear in X. Sometimes we assume that F is degenerate, like in the very simplest Russ model. The mileage goes up by one mile or 1,000 miles, whatever it is. So quasi-maximum likelihood. Just go ahead and estimate F using theta 2. Now define your kappas using the weighting scheme that I was talking about. Rush through a little bit, but it's a kind of a flyover view. Got the value correction terms, you know, those log P things in the type 1 extreme value. By using the cell estimators, put the value functions together, plug in the P's by substituting for the value functions using the inversion theorem, and just go for it. So we've got that the value function is just equal to, here is conditional value function estimated. Here is our utility function plus this H term. This is the numeric dynamic correction factor. Remember from the Mr. Zerker problem, it was just the ratio of the logs. More generally, you've got to worry about this thing. Bigger object, but it's all numbers. Computer's good at adding and subtracting numbers. It's not good at nonlinear optimization. So you put the kappas together, and in type 1 extreme values, we've already talked about that. Okay. Here's that H that we were talking about before. It was the log of the P's in the Rust case. That's how you would do it. Another approach, and this is going to be discussed by Hank later on, is a minimum distance estimator between the unrestricted estimates and the restricted estimates. So go away and first of all, get the unrestricted estimates, okay? Get the unrestricted estimates using the conditional value function stuff that we talked about back here with the, I won't go back, with respect to that representation. Here it is, the differences between those two, okay? It's a little bit hard to see here, but what I'm doing is subtracting the j from the first, and that's why I've got this subtraction going on here. Estimate the reduced forms for the p hats and the f's, and then say, okay, we've got the unrestricted estimator, which we actually talked through when we did the identification. We talked about how do we get the differences in the u's? Well, we just difference out the b's. That was the theorem thing. Now, all we're doing is putting functional forms here on the unrestricted quadratic form, okay? And notice that this is a quadratic form, so if these things are linear, this means that this is going to be a linear estimation problem, okay? Thing is going to be talking about some of that later on, I think. So that's how you would get a minimum distance estimator out in this case. Really, what we're talking about in principle is either cell estimators or smooth estimators for the conditional choice probabilities and the transitions, forming this new thing numerically, and then saying, okay, make this a linear in theta. Obviously a closed form solution, least squares actually. Or we could do simulation estimation. Here in this case, we simulate a lifetime out using the F's and the P's. Think about what the guy's doing. There's a probability that he'll move in these different directions, different ways throughout his life. We just use his conditional choice probabilities to get out the distribution of what he would do, okay? So we can simulate it, right? Because we see the probability of moving one way or the other way at each of these periods. So why don't we just simulate out his life, okay? We can do that. I'm going to do that next period. And then where all the assumptions come in, I think, is where you're looking at the expected value of the unobservable. And the reason why they're coming in there is because you're taking the expected value of an unobservable conditional on a choice, which is the optimal choice, and that's where you need these distributional assumptions about the epsilons in order to be able to get this, okay? And this ties right back to the selection literature of Heckman and others back in the 70s, where in discrete choice models, you have exactly the same problem. So you get the expected value of this conditional expectation of the epsilon, given that the person is making these different choices. And on this J minus 1 dimensional vector, almost same, to get those v hats, okay? And then we go from there by, here we have the difference in the conditional value functions with the correction factors appropriately. Go from there with an instrument vector. Again, go ahead. And you would find in this situation as well that if utilities are linear, well, then this also has a closed form solution. The first one, the quasi-maximum likelihood, is not closed form, but it's just logic. So you're still talking about a concave objective function here, fairly straightforward to get to. We should stop. I'm 2 minutes late. So let's have a break for, what is it, 10 minutes? Is that correct? 15 minutes, thanks, Juan. 15-minute break, and I will start maybe 2 minutes late, okay? And I will finish on time, though, promise.